Hi guys, my name is Arturo Misael Villarreal, and I did this project talking about set constructions for my Math 3371 Communications in Math class, which is a class in Texas A&M International University for the year and semester of fall 2022, and I was advised by my professor, Mr. Juan Arellano, while constructing this project. In the outline, let me give you a little introduction about the outline. The outline consists of the abstract, the introduction. In the abstract, I'm gonna give you my whole idea as to why I created this theory and what not created this theory as to why I created this project, and basically the whole idea of what my project consists of. In the introduction, I'm gonna give you about what is a theory, and I'm gonna talk about the founder. In the history, we're also gonna talk about the founder and how he arose with this theorem. In the math tools, we're basically gonna talk about what a set consists of, so basically we can have a little bit more understanding of what set construction can be. For the guided project, we're going to talk about the two main ideas, which is successors and the axiom of infinity. These two things, these two ideas, these two components are basically the general idea of set theory. In the narrative, we're going to talk about basically what was my whole concept, what was my whole thought after I created this project. And for the references, there were too many references, but we received the references from the JSTOR website and also from our book. Let me give you a little let me give you the information over from my abstract. Well, the purpose of this project was to state what set construction is. As we know, set construction is basically, let me give you an example. For example, let's say TAMU. As we know, in TAMU we have different groups, which can be professors, which can be students. However, under those groups we have some subgroups which can be, for example, professors. We have the adjunct and we have the full-time professors, and under those we have several elements or professors, which can be professors that have a PhD and professors that have a master's degree. On the other side, for students, we have a group of students which can be a subgroup of undergraduates and graduates, which can have elements of being freshmen, sophomores, juniors, and seniors. And this is basically a little description of what set theory is, because all these groups of elements are together in a set, and it's basically defining the whole set being TAMU. Cardinality. Cardinality was invented by Georg Cantor, and basically it was the foundation as to set theory, but I'll explain a little bit more of that in the introduction. Introduction. Let me give you the introduction about set construction. It said the set construction is basically that approach where several elements can be part of a set. Basically, we have several sets that can be either infinite or that they can be finite. When we talk about infinite sets, it's basically, as we know in Calculus 1, we learn about limits, and we learn that some limits may approach infinity. It is basically all those sets that basically have too many elements. For finite sets, it's basically are those elements that are countable. Cardinality is basically the foundation of the set theory of set construction, because we know that cardinality is basically that idea that counts how many elements are part of the set. if cardinality wasn't invented, meaning that basically mathematicians wouldn't agree with the idea that we don't need to use the English language or English words. Let me go back to a little bit introduction about English. Basically, we know that in English we consider the idea that a sentence consists of either a noun and a verb. Basically, in set theory, we know that we don't need to use what is it called? Sentences to write down sets, that basically they can be symbols to express several elements being part of the set. Let me give you a little introduction about the history. Well, everything was founded in the 1800s by a famous mathematician, which his name is Georg Cantor. Georg Cantor was one day playing with sets. He was like basically inventing or researching that what can be a shorter way to express or to show that several elements were part of the set. Basically, he did not want it to write, for example, let's say numbers from 1 to 10. Basically, he didn't want to put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Instead, for example, he could have put n being the number greater than or equal to 1. That was the shorter way. He found that a set can either be finite or infinite, meaning that when a finite set is something that is countable, while an infinite set is something that is not countable, meaning that it has too many elements for that set. He also arose with the idea that there were elements, that there were symbols to show that there can be too many elements for that set, or that there's only certain elements that work for that set to be true. For example, one of them is the upside down A. That one, that means that for all the elements stated in the set will be true. But the E that is reflected across the y-axis, I don't know if you've seen it, but it's the one that goes like it's an E backwards, basically. It states that there's a certain element for that set to be true, meaning that it is a finite set. For the math tools, basically in the math tools we basically have sets, element, infinite, and infinite. While sets is basically that collection of elements, which cardinality says. Elements is basically all those numbers or symbols that are part of the set. For example, for elements and set, for example, let's say for a set, let's consider the kitchen. For example, an example can be the kitchen of our house. We have the whole kitchen being our set, but for the elements, we have the chair, we have the table, we have the dishwasher, we have the plates, cups, knives, spoons. That's a little thing of how I see sets. For example, in a room, we have the whole room being the set, but under the element, we have our bed, our pillows, our TV, our clothes, and stuff like that. An infinite set and infinite set is basically, as we know, infinite, too many, and infinite, countable. And set construction is basically all those elements that are part of the set, and that's how the set is constructed. Cardinality, we know that it was because of Georg Cantor. We wouldn't arouse with the idea that there's a shorter way with symbols and math to express the construction. We know that cardinality stands for all those elements cardinality stands for the idea of counting the elements in the set. And we have subsets and supersets. Subset is basically when we have a set A where B is an A, then A is a subset of B. Supersets when we have a set A where B is an A, then A is a subset of B. Then since all elements of B are in A, this means that B is the superset of A. Since all elements of B are in A, B is a superset of A. Let us go with the idea of successors. Successor is the biggest component for set construction and set theory. As we are knowing a function, let us consider the function Sx equals x plus 1. If we were to plug in for every x a 0, we know that we receive the 0, 1, and then we plug in 1, we get 1, 2, because 1 plus 1 is 2, and then for here we plug in 2, we get 3, and then we get 2, 3, right? Basically, in set theory, this cancels, and we now get basically an idea of a set being an empty set, and it goes on like that. Let me give you a little bit more introduction, a little bit more detail. For example, at S0 we have 1, but in set construction it is set theory or set construction, meaning, for example, this is the same thing as saying this. However, this is numbers, this is sets and elements. In sets, we have that at S0, which is the same as S0 over here. We know that S0 it will be the same thing as an empty set. At S1, we have the empty set and 1, and then at this we have the third step, which is basically this being inside this, and then this being inside of the third step. And we have the empty set, then we have 1, and then we have 2. And this is what it leads, that for x to the plus, we have x being in union with all the previous elements, and that is what arouses it with the axiom of infinity. But the shorter version of explaining the axiom of infinity will be that basically in set theory we have that for every new step, for every step, what I'm talking about every new step, I mean by this is one step, this is the second step, this is the third step. For the third step, we're going to have the elements of the second step and the first step already being included in step number 3. And basically it's going to continue until it reaches a certain step where all the previous elements will be part of this new step, and that will lead to the idea of the axiom of infinity, because in the axiom of infinity we're going to reach a step where all the previous steps are going to be part of the new step. However, at the third step it will be the end. Basically, in this project, I hope to give you all the very my best research over set construction. It is understandable when people do not want to see numbers and they just want an actual definition or to get to the point. Successors is basically all those elements that come over after the first element in the set. The axiom of infinity is basically every successor after 0 leading all the way to infinity, which will be the last step in R, or in my explanation. These are my references, and I would like to express my gratitude to my advisor, which is Mr. Juan Arellano, for helping me in this project and for everything he did for us during the whole semester. Thank you. If y'all have any questions, please let me know. Thank you.